Good day, good day, good day, everyone. And once again, we are back together. All right, and today we're going to be looking at the physical science paper one for May June exam, right? That is 2024. So if you haven't subscribed, please just make sure that you're part of this family, right? And for those of you that need assistance, you can get in touch with us. We've got all our services. You can come through to our center, but all the information that you need will be on the description of this video. All right, so let's dive right into it. We're going to start with the multiple choice section. Okay, let's get into it. They say a book rests on a table. Which one of the following forces will form an action-reaction pair with the weight of the book? Now remember, what is the weight of the book? The weight is the force of the earth that the earth rather exerts on the book, right? So in this case, it means that the action-reaction pair, just like Newton's third law states, right? If body A exerts a force on body B, then it's going to be body B on body A. So in this case, okay, if it's earth on book, right, then it's going to be book on earth. So I believe that will be option B for that one, right? And then they say a person is standing on a bathroom scale in a lift. Which one of the following which one of the following motions of the lift will result in the smallest reading on the scale? Now, just for you to note, ladies and gents, actually, what the scale usually reads, if you're looking at an object or someone that's on a lift, okay? So let's say there's a scale there and the person is standing. Now, if the lift is stationary, right, that means that the force that is read on the scale will actually be the weight of the person, or if the lift was moving at constant speed, right? But now once the lift moves or accelerates upwards, right, so this is the force that is exerted on the lift, and this would be the weight. Okay, so in this case, if the force that lifts, okay, is actually much greater than the weight, okay, so what will happen is that, of course, I know that we will accelerate upwards, and so what will happen is that in this case, the reading on the scale will be much greater, okay. So if the lift accelerates upwards, the value will actually be greater. Now, they want the value to be the smallest. So in that case, it means that the lift has to be accelerating downwards. Okay, so let's look at this. They say the lift accelerates upwards, the lift accelerates downwards. Okay, I would go with B, but let's look at the other option. Okay, the other options say constant velocity. So I definitely say B is my answer. All right, now the next one, they say the velocity versus time graph below represents the motion of a ball which was in free fall. The ball struck the ground after 3t seconds. Right, they say which one of the following statements is correct. Okay, they say the ball was dropped from a height above the ground. Okay, right, we'll just have a look at that just now. I would tend to be, well, not dropped, but it was actually thrown because its initial velocity is really not zero. Okay, so yes, it was above the ground, but it was not dropped. So thrown vertically upwards from the ground, not true, because in that case, I can see that where we threw it from, right, it didn't come back to the same place, okay, but it actually passed it. All right, and then they say thrown vertically upwards from a height above the ground. All right, I think I can go with C, but let's look at what D has. They say thrown vertically downwards, okay, from a height above the ground. Now, if you look at this, the reason why I'm saying vertically upwards, now note that it must have reached maximum height at this stage, right? So we threw it, right? It went up, reached the maximum height, and then started coming down. Now, in this case, it must tell me that as much as I threw it upwards initially, but I took down as positive, right? Why? First of all, my gradient is positive, and in this case, my initial velocity is negative, which tells me it was upwards, right? So, in this case, the correct answer there would definitely be option C. All right, now let's go to the next question. They say the vector diagram shows the initial momentum, right, P1, the final momentum P2, and the change in momentum for the car that moved on a straight horizontal road. Now they say which one of the following sketch graphs correctly shows the momentum of the car for the time that the car moved on the road. Now, first of all, note, ladies and gents, okay, so the momentum before, or in this case, the initial momentum, was greater than the final momentum, right? But both in the same direction. And so the initial momentum, the change in momentum would be negative because final minus initial would definitely give us something that is in the opposite direction. Now, let's look at which one is a correct interpretation. Okay, so initial momentum must be bigger and positive. So the only one that seems to suggest that is option A. Right, so you can see our P1 is bigger, and that is P2. And certainly if you take P2 minus P1, you will get a negative answer. All right, so the next question, they say a stone of mass M is dropped from a height h above the ground. Ignore the effects of friction. Right, now they say which one of the following combinations in the table below correctly represents the kinetic energy and the total mechanical energy of the stone at the instant the stone has fallen through a distance 1/4h. Now, ladies and gents, let's suppose that in this case, remember they've given us the mass and they've also given us the height there. So that means that from the moment when I dropped it, okay, in this case, my potential energy, mgh, remember, at the moment when I reach the ground, right, that means that the kinetic energy would actually be equal to the potential energy over there, right? Now, remember, what are they asking us? We want to know when it has fallen a distance of 1/4h, right? And in this case, what are we going to notice there? So we're going to say, right, what would be the kinetic energy at that point? So we're going to say, right, still our initial potential energy is mgh, but now it falls a quarter of the height, okay? So which means that the height that is left there would be mg times, now think about it, would have fallen a quarter, so that's still 3/4 of that height over there, right? So that's what we would have fallen. So I want to find out what would be the kinetic energy at this point over here. All right, so I'm going to say, right, so that's EK, right, at this point here would be equal to, right, the potential energy initial minus the potential energy, the potential energy final minus the potential energy initial. So in this case, it's going to be mg. Now remember, our final potential energy was 3/4h, right? And this is minus that 1h, right? So that would be 3/4h minus 1h. Okay, so minus 1h. So meaning the kinetic energy will actually be a quarter, right, of what it can be when it gets to the bottom there. Right, so in this case, this is going to be 3 over 4 minus 1. That would be 1 over 4 mgh. So I'm going to choose 1 over 4 mgh. So that would be somewhere between the two. But they're saying, what is the total mechanical energy? Right, so it should be mgh because that is what we started with. That's the total. Our kinetic energy was 0 at the top. Our total mechanical energy will be mgh. So in this case, EK, 1 over 4. And, okay, so it looks like our answer should be D. Right, I hope that you can appreciate the explanation, guys. Right, as we go to the next one. They say the spectrum of helium emitted from a star moving away from Earth is compared to the spectrum of helium found on Earth. They say which one of the following statements is correct. Right, now first one, they say the observed spectral lines from the moving star will have A. Now note in this case, they said that the star is moving away from the Earth, right? So we know that for objects that are moving away from the Earth, right, we are going to have a red shift, okay? So we're going to shift towards the lower end of the frequency spectrum, okay? And of course, we know that it will be longer wavelength. So in this case, let's see, lower frequency, definitely, yes, actually, lower frequency and a longer wavelength, definitely that does look like the answer, okay? Higher frequency, all right. So A would actually be the correct one. Right, the next question, they say the magnitude of electric fields generated by different point charges are measured at a fixed point, right? They say for each measurement, the distance between the fixed point and the charge are the same. Okay, now note, what are we doing? We are comparing a charge, right, or electric field versus charge. And we know that if we look at the formula, right, there's a direct proportion in terms of their relationship, right? And they did say that the distance is kept the same, all right? So what would be that relationship there? It would definitely be the relationship A, right? So it is directly proportional, right? So the next question, they say the diagram below represents a circuit in which all the external resistors have the same resistance. Right, now they want to know which one of the emitters in the circuit will have the lowest reading. Okay, so which one would have the lowest reading? Now definitely not A1 because no A4 because that's the total current, okay? But we know that current divides when it gets to this node. Some of the current goes here and some of the current goes there, right? Now in which branch do we have the highest resistance, right? Definitely we'd have the highest resistance here because there are two resistors. Remember, more resistance means less current. So at the end of the day, it means A3 will actually give us the lowest reading. And so that is option C. All right. And 1.9, they say we've got a simplified diagram of an electric machine, which is shown below. Right, the type of machine that this is, okay? Now note, first of all, we've got a battery there. So remember, battery will supply us with current, okay? And in this case, I also see that I've got split rings, okay? So this tells us that we've got DC over there. But now, the fact that we've got a battery tells us that this is not a generator, but it is a motor. So I will say, well, this is definitely a DC motor. Okay, and finally, They say which one of the following combinations is correct for a line absorption spectrum in which the energy transition of the atoms and the appearance of the narrow lines in the spectrum, right? So we're looking for a line absorption spectrum. So we know that in that case, okay, that the transition, in order for it to be absorption, we are moving from the lower energy levels, right, to the higher ones so that they absorb energy. So lower to higher energy states, right? And because it is an absorption spectrum, what are we going to see? We're going to have dark lines that are appearing there, right? We are not having line emission, so lower to higher, that would definitely be dark lines that appear. And so the answer is 1.10, all right? I mean, in 1.10 rather is C. And so as a result, that is really how the cookie crumbles. Right, let's go on to question number 2, and we are going to be looking at it. Okay, and please note, don't forget to subscribe if you still haven't. Let's go to question 2. Right, so in question 2, they say block A of mass 4.1 kilograms is connected to block B of mass 2.3 kilograms by light inextensible string passing over a frictionless pulley. Right, they say block A is at rest on a rough horizontal table rather, and they say block B hangs vertically as shown in the diagram. Right, now they say we've got a force F of magnitude 49, which is applied on block A at an angle of 50 degrees to the horizontal, causing A to accelerate to the left. All right, that is definitely very important. So we know that A would be accelerating in that direction. So we might as well just say, for A, that's our positive direction. Now, if A goes to the left, automatically it means B would be going up. And so for B, upwards is positive. Right, so they say the coefficient of kinetic friction between the table and block A, or the surface of the table and block A, is 0.35. All right, now let's try and answer the questions. It says state Newton's law of motion in words. Okay, we know that the resultant force is equal to or directly proportional to the rate of change of momentum. Okay, right, of course you can always give that longer statement on Newton's second law, right? If a resultant force acts on a body, the body will accelerate in the direction of the resultant force, and that acceleration is directly proportional to the force and inversely proportional to the mass of the object. Okay, right, so they say to us, draw a labeled free body diagram showing all forces acting on block A. Right, ladies and gents, I'm going to try and answer these questions as much as possible on here. All right, but of course, if the need arises, we might actually just try to create some space elsewhere. Right, so first of all, what do we have? We've got force F. This is the applied force. Okay, and then on the next one, which other force do we have? We've got the tension on the string. So I'm going to say tension on string. And please, ladies and gents, please label in full. Okay, so in this case, we've got the gravitational force. Okay, so there we go. That's the weight of the table. I mean, the weight of block A. Right, so let's say weight A. And then we also have the frictional force, right? So we are unsure at this stage as to which one is bigger than which, but we know we've got the force of friction there. So that's frictional force. Okay, and that is essentially all the forces that are acting. Is there anyone that I've left? Okay, oh, actually we left out the normal force. Right. And please note, ladies and gents, there's always an indication as to the number of forces based on the Mach allocation, right? So that Mach allocation already was telling me that there's something that's missing there. All right, the Mach allocation is 5, so that's 5 forces that we must see there. All right, there it is. We've got all our forces. Now, they say to us, calculate the magnitude of the kinetic frictional force exerted on block A. Now, ladies and gents, I want you to please note this. To calculate friction, right, so we need to find out what the normal force is. And the normal force is one of the forces that are vertical, right? Now, remember that, so what I'm going to do, just for the purpose of making sure that we don't mess up our diagram, please remember that the applied force can be broken down into components, right? So it's got FAX, which is the horizontal component of the applied force, and I'm going to also say this is FAY, which is the vertical component of that force. Okay, so those two forces acting together are the equivalent of the applied force. So we can replace those two red forces for that one force, which is the applied force. Okay, right. Now, I want you to note, then, what does it mean? Which forces are vertical, right? We've got the normal force, we've got the weight, we've got the vertical component of the applied force. So then I'm going to say, right, in this case, note that those three forces are actually at equilibrium. Why do we note that? Because our body is not moving vertically. So I'm going to say, well, we're going to say F net, right, equal to MA, but we're taking the sum of forces in the vertical, and this is equal to 0 because the body is not accelerating vertically. So this is going to be force applied, right? The vertical force applied. So I'm going to take forces going up as positive. So it's going to be FAY, right? Plus the normal force minus the weight on A, and this is equal to 0. Right, now I want you to note in this case we are looking for the normal force. So the normal force would be equal to, now please note, ladies and gents, that's going to be the weight, right? If I take that side, it becomes positive. So that's going to be mass times G minus, now note, remember, we would have had our angle there, which is 50 degrees. So this is going to be FA, the sine of 50 degrees, right? And now, can we calculate our kinetic friction? We absolutely can, right? We've got the coefficient of friction, and so that means that the frictional force will be mu k, coefficient, multiplied by the normal force, right? So this would be 0.35 into, right, mg, so that's 4.1. Okay, let's take that, 4.1 multiplied by 9.8, so that's 40.18 minus, right, so we've got the coefficient of friction, so this is going to be 49, the sine of 50. Okay, all right, so I'm going to take that entire thing. In fact, we might as well just calculate that whole thing. So 0.35 into 40.18 minus 49, the sine of 50 degrees. Okay, right, I get a force of, so friction, in this case, is this correct though? Okay, so I get a force of friction of 0.93 newtons. Okay, that's our value for frictional force. Okay, so please just note there. So on the last one, they said to us, sorry, I didn't finish writing this entire one. So it was friction, that's mu k, times normal force, that's 0.35 into, remember we had said mg, that was 4.1 times 9.8 minus f, which was 49, right? The cos, rather the sine of 50. Okay, and that's how we got 0.98, if I remember, or 93 rather, newtons. All right, now let's go to the next one. They say calculate the magnitude of the acceleration of block A by applying Newton's second law to each of the blocks, right? Separately. Right, so starting with block A, let's look at the forces that are there. So we know that we're going to say F net is equal to MA. So the sum of the forces in block A, right? The sum of the horizontal forces. Now note, it's going to be FAX, right? The horizontal component of the force minus the tension minus the friction. So we're going to say this is going to be FAX minus friction minus the tension, and this is equal to MA. Right, so FAX, that's going to be 49. The cosine, remember that's on the adjacent side of 50, minus the friction, we said that's 0.93, minus the tension, which we don't know, is equal to 4.1 times A. Right, so we can try to simplify that as much as we possibly can. And that gives us 49, the cos of 50, minus 0.93. Okay, we get 30.57. Okay, minus t, and this is equal to 4.1a. Right, now let's go to block B. So for block B, remember we said block B was going upwards, and what's pulling block B? It's that tension, but we know we also have the weight of block B. So for block B, we're going to say tension minus the weight of B is equal to, so that's MB times A, right? So that's tension, we don't know it. The mass of B is 2.3 times 9.8. This is equal to 2.3 A. So this is going to be, let's say this is our equation 1, and that is equation 2. Now nothing wrong, ladies and gents. You can make T the subject of the formula and substitute. But what I normally do is to take equation 1, right, and equation 2, right? So we note, or rather equation 1 plus equation 2. So just add the two equations together. So you're going to have 30.57 minus t, right, plus t minus, now if we took 2.9 multiplied by 9.8, okay, 2.9 times 9.8, and that will give us 28.42, and this is equal to, right, if we add the right hand sides together, 4.1 plus 2.3, that will give us 6.4, and so that becomes 6.4a. Right, so ladies and gents, how it always works out is that you will always cancel something there. So I've got 30.57 minus 28.42 and in this case we get 2.15, and we're going to divide by 6.4, and I get an acceleration value of 0.34 meters per second squared. Please confirm if you get the same answer, right? That's what I get on my end, right? As we are going to look at the next question. Okay, so jumping into question number 3. So they say we've got a hot air balloon that moves vertically downwards at a constant velocity of 3.4 meters per second. They say when the hot air balloon is 15 meters above the ground, a small ball is dropped from the balloon. They say refer to the diagram below. Right, now we can see there's our small ball there. I've tried to highlight it in red. Okay, so they say the ball strikes the ground and bounces vertically upwards. Okay, so we know that we're going to get this guy coming down and it's going to bounce. Okay, vertically upwards. The hot air balloon continues to move downwards at the same constant velocity. All right, now they say ignore the effects of air friction acting on the ball. Define the term free fall. Now remember that free fall refers to the state of motion of an object under the influence of gravitational force only. Okay, right. So the next question, they say the sketch graph below, not drawn to scale, represents the position of the ball relative to the ground from the time the ball is dropped until the time it reaches its maximum height after the bounce. Now, ladies and gents, please don't be alarmed by this drawing. So what they've done is essentially, right, they have taken downwards, in this case as positive. Now remember, where was the ball initially, right? It was 15 meters. So this is what they are trying to say. It was 15 meters above. So if this is our reference, the ball and the ground is our reference point. So the ball is not above the ground. It's not below the ground, in which case it would have been positive, but it is above. Okay, so in this case, relative to our reference, which is the ground, it is on the, and I quote, negative side. I'm using inverted commas, right? So in this case, it means that that's what the diagram is telling us. So meaning when the ball initially dropped, okay, it was at a height of 15 meters above the ground. Okay, and this is where it gets to the ground. This is when it leaves the ground, and this is when it reaches the maximum height. Okay, so they say, was the ball in free fall at T1? Okay, at T1 to T2 seconds, write down yes or no. The answer is a definite no, right? And why is that? This is when the ground, the ball was on the ground, and remember, once it lands on the ground in this case, there's obviously the force that the ground exerts on the ball, right? The normal force in that case, and so it is no longer in free fall. Okay, or we can say that gravity is not the only force that acts there. So they say to us, use only equations of motion to calculate the value of T1, okay, indicated on the graph. So when it arrives on the ground, okay, so we know, firstly, we know its initial velocity. What would be the initial velocity? Ladies and gents, it is very important. As much as they say to us it was, I'm trying to look for it, they say the ball is dropped, right? But remember, the ball is dropped from an air balloon that was already moving at at a velocity of 3.4. So the velocity of the air balloon, the initial velocity of the air balloon, will not be 0, but it is going to be 3.4 meters per second. And remember, I said to you, they seem to have chosen down as positive, so I will maintain that choice. right? And then what about our final velocity? That's what we are looking for, isn't it? They wanted us on, actually they wanted to find out the time and when it reaches the ground. So gravitational acceleration, that's positive 9.8 meters per second squared. The time, that's what we want to find out. Okay, but we know what is the displacement from the top there, right, all the way up until it reaches the ground. We know it is going to be displaced 15 meters. Now, this is me using the point of dropping as a reference. So it's going below that point, which means it would be positive. So this would be positive 15. All right, now, ladies and gents, we are almost there, right? So in this case, we want to find out which equation are we going to use. Well, it would be the only one without a final velocity, right? So let's try and do that quickly. So I am going to say delta y. Okay, that's initial velocity, delta t, plus 1 over 2 times g delta t squared. Our displacement is 15. Our initial velocity is 3.4, right, time delta t. Okay, our g value is 9.8, and this is multiplied by delta t squared. Now, of course, this gives us a quadratic equation. A half of 9.8, that's 4.9, plus 3.4 delta t, right? And in this case, minus 15, and this is equal to 0, right? So we know this is 4.9 t squared. That's 3.4 delta t. That's minus 15. Now, what I want us to do, we can use the quadratic formula in this case to try and get that answer. So this is going to be delta t is equal to minus 3.4 plus minus the square root, right, of b squared, which is 3.4. That's 3.4 squared, minus 4 times a, which is 4.9, multiplied by c, which is minus 15, right? So all of that is under the square root, and this is divided by 2 times 4.9. Okay, right, so let's try to get that. So that's negative 3.4. I'm going to start with the one with the positive, plus the square root of 3.4 squared plus 4 times 9.8 times 15. Okay, and right, let's find the answer there. Okay, this gives us, okay, divided by 9.8, 2 times 4.9, that's 9.8. Okay, so I get a time value, right? I'm not going to bother looking for the other one because it gives me a negative value, right? So this would be a time of 2.15 seconds. Absolutely nothing wrong, ladies and gents, with going to find the final velocity first and then calculating time. Nothing wrong with that. Right, let's go to the next one. So they say the height of the air, or they say rather, calculate the height of the hot air balloon above the ground at the instant the ball struck the ground. All right, now remember that the balloon is moving at a constant speed of 3.4, right? So which means its acceleration is 0. Its acceleration is 0. So in this case, it means that, right, so how long did it take? It took 2.14. Let's find out how long the balloon would have been from the ground. So first of all, going to say delta y. That's v delta t, right? But remember, half a delta t squared. Remember we said acceleration is 0, so it takes out that entire term. So delta y, that's what we want. Our velocity is 3.4 and our time is 2.15. Okay, let's find out. Okay, so we get 7.31 meters. So the ball had traveled a displacement of 7.1 meters. But remember, from where it fell from, it would have traveled a displacement of 7.31. But what are we looking for? We are looking for the height of the hot air balloon, right? Actually, I said the ball, but it's the hot air balloon, right, above the ground. So we know the hot air balloon has traveled 7.31, but how far was it at the beginning? It was at a height of 15 meters. So therefore, the height will be 15 minus 7.31. And what do we get there? All right. This guy is misbehaving. Okay, I get a value of 7.69 meters. That's the height that would have that the ball would have fell, right? So in that case, that is really how the cookie crumbles. Okay, let's go to the next question. They say the ball was in contact with the ground for 0.2 seconds and left the ground with a velocity upwards, a vertical upwards velocity of 7.2, right? They say use only equations of motion to calculate the value of T3 indicated on the graph. Now T3 would be when the ball reaches its maximum height, right? So what I'm going to do there is I know that from the time that the ball left the ground, okay, its velocity was 7.2, that's what they told me. But when it reaches its maximum height, the velocity there should be 0, okay? And by the way, we're looking for time, and we know that gravitational acceleration is 9.8. Okay, so in this case, because we're looking for time, I am going to simply say VF. Okay, so our final velocity is 0. This is when it gets... now remember, we already had chosen down as positive. Okay, so initial velocity, our ball was actually going up. Okay, this is plus 9.8, and we're looking for the time. Right, so take this to the other side. 7.8 equal to 9.8 delta t, and divided by 9.8. And so the time would be 7.8 divided by 9.8, and that gives us 0. Well, let's just say 0.8 seconds. Okay, right. Now note, this has absolutely nothing to do with that time there. This would be the time in contact with the ball, but we are looking for T3, right? So remember, we now know the time it took over there, right? We know that that time was 2.15. So this time would be 2.15. Now we know T1 to T2 is 0.2, Okay, so plus 0.2, this would give us 2.1. So this would actually 2. Not 2.1, 2.35. Now we're saying we are now going to add the 0.8, right? So from T2 to T3, that's 0.8, but we are adding it to 2.35. So T3 will be 2.35 plus 0.8, and so that becomes 3.15 seconds. Right, I hope that makes sense, ladies and gents. Right, so we found the time T2 to T3 first, and we used that time and added it to the other times as well. All right, and we would have earned ourselves 14 marks, and really that's how the cookie crumbles. Right, on question number 4, they say two trolleys A and B of mass 3.2 and 2.6 kilograms respectively are held at rest on a straight, horizontal, frictionless track with a compressed spring between them as shown in the diagram below. Now they're asking, after the trolleys are released, right, the spring extends to its natural length and then falls onto the track. They say trolley A now moves with a constant velocity of 0.4 to the left, as we can see there on the diagram. And they say while trolley B moves with a constant velocity to the right, they say trolley B reaches the end of the track after 1.3 seconds. All right, now they say state the principle of conservation of linear momentum in words. Right, please note we say that in an isolated system, the total linear momentum is conserved, right? Okay, or you can say momentum before collision equal to momentum after collision in an isolated system. Right, so they say calculate the distance traveled by trolley B. So in order for us to calculate the distance traveled by trolley B, we would have to find out the velocity of trolley B after collision. Right, so let's look for some space here. Okay, so let's do it over there. So we are going to say, so momentum before collision equal to momentum after collision. So sum of their momentas before collision, so you can say initial, right, is equal to the sum of their momentas after collision. Right, so now, first of all, what was their momentum before collision? Remember, the entire system was stationary, right? They said before it is released, and we know they are held at rest. So both trolley A and trolley B were stationary. So in this case, the total momentum before will actually be 0. But then after collision, we know we've got individual momentas. So I'm going to say MB, VB, that's final, that's final. Right, so now please be careful to always choose a direction. Right, I'm going to stick with taking right as positive. So I'm going to say right. So for A, which means A after collision moved in the negative direction. So that would be 3.2 times negative 0.4, apologies there, 0.4, plus B would be 2.6, right, times the velocity of B final. All right, so let's try and get that. So 3.2 times negative 0.4, and 2 times 0.4, I get 1.28. And remember, when you take it to the other side, it becomes positive, whereas it would have been negative here. So we've got 1.28 positive is equal to 2.6 VBF. And so we can divide both sides by 2.6. and I've got 1.28 divided by 2.6, and I get a value of 0.49. Okay, so we get the velocity of B would be 0.49 meters per second. But remember, what am I looking for? I'm looking for the distance that will be traveled. Since this is constant velocity or constant speed, I can say, well, delta x would be v times delta t. My velocity is 0.49 and my time is 1.3. Okay, and this is 0.49 multiplied by 1.3, and we get a displacement value of 0.64 meters. All right, so that would be the distance that would be traveled by trolley B. And remember, because we actually know that it's constant speed, it's a frictionless surface, right? All right, so let's go to the next question. They say to us the average force exerted on the on the extended spring, right, on each trolley while they were in contact with the spring was 4.2. Okay, they say calculate the time it took the spring to extend to its natural length. All right, now I want you to note, ladies and gents, we are now looking at the amount, and by the way, please note, so were we given, in this case, the time that it took for the spring to extend? All right, let's look at this. So this would be from 0 to 1 point, or rather, it's from 0, rather, the average force exerted. So now, in this case, we're going to simply say, right, if we're looking at the spring that is released, okay, I'm just trying to see here. Right, we're gonna have to take the change in momentum of each, right? Of one of the trolleys, of one of the trolleys. So let's take the change in momentum of trolley A. So I'm gonna say F net times delta t is equal to change in momentum. Right, I know the force that would have been exerted is 4.2. I want the time that it takes, right? And this would be, right, remember I said I'm taking for trolley A. Okay, so in this case, the mass is 3.2. Final velocity for A is 0.4, but remember I told you that I took the right direction to be my positive direction. So that would be negative 0.4 final, right? Minus my initial velocity was 0. And so what happens there, I'm going to divide both sides by 4.2 so that it cancels with that. And I've got delta t, which is equal to, so I'm going to have 3.2 times the negative 0.4. Okay, and this is divided by the 4.2. Okay, so which means the time it took, and by the way, please don't mind about the negative. In this case, I was supposed to actually put that force there as negative as well, because it would be a force that will be pushing to the left. So the time would be 0.3 seconds. I hope that's clear. Nothing wrong if you decided to take body B. You would actually get exactly the same amount of time. Okay, so let's go to the last portion. They say trolley B is now replaced with trolley C, which has a larger mass. The same compressed spring is placed between trolleys A and C. The trolleys are then released. The average force exerted on the by the extended spring on the trolleys remains 4.2 for the same period of time, right, as calculated in 4.3. So they say now, how does the magnitude of the velocity of trolley C compare to the magnitude of the velocity of trolley B after the spring has fallen on or to the track, right? So they say only write greater than, less than, or equal to, and then we must explain that answer. Now remember, we know that trolley C has a larger mass, okay? And remember, in this case, according to Newton's third law, or rather second law, it will have a lesser acceleration, right? So the change in momentum will be much less in that case. So they said to us, how does the magnitude of the velocity? So it would be less than. Okay, right. Now they said to us, we must explain. So we know that F net is equal to m multiplied by the acceleration. Okay, so let's show that. So if we're looking at acceleration, that would be net force divided by the mass. So we can state that the greater the mass, okay, in this case, the lesser the amount of acceleration that would be experienced for the trolley. All right. Alternatively, we could use the impulse momentum equation, the one that we just used. Right. We said that F net would be change in momentum divided by change in time. Right. And so note in this case that change in momentum, that's m times change in v over change in time. Okay, so what did we do here? We said, well, we made the mass of B much larger. Okay, so I actually wanted to show it from change in momentum. Okay, so we made, in fact, I think this would actually show it much better than this one would. Okay, so that means that the greater, in this case, the mass, okay, and what would happen there is that the change in velocity would be actually less, all right, and so resulting in a change of velocity being decreased. Okay, right, I hope that makes sense, ladies and gents. Right, I think I would go with this one in terms of my explanation, all right, but we know it definitely will be less than. All right, let's go to the next question. And so on to question 5, they say to us, we've got a crate of mass 18 kilograms initially at rest. Now, what I always like doing, ladies and gents, is just to show, I'm going to say, well, the velocity of the trolley is 0 over there. They say it slides down the slope from point A to point B. The crate then moves along a rough horizontal surface, okay, from point B towards point C. Point A is 3 meters above the surface, horizontal surface, and in this case, they say, right, we see the diagram that is below. Right, now note, very important to note there, that this is a frictionless slope, right? So there's no friction there. And this crate is essentially just sliding there. There's no applied force and there's no frictional force. Now they say to us, state the principle of conservation of mechanical energy. Very good that they are saying that, because remember, between A and B, we will apply principles of conservation of mechanical energy. Right. Now, if you look at this, we are going to say, all right, so EMEC, all right, or the mechanical energy at A, oh, by the way, that's for the second one. Remember, the principle simply states that in an isolated system, the total mechanical energy remains the same. So, they say using principles of using energy principles only, calculate the speed of the trolley at point B. So this is where we're going to say Emac at A is going to be equal to Emac at B, right? But note at A, we've got kinetic energy, we've got our kinetic energy is 0, but the potential energy would have a specific value there. But once we get to B, our potential energy is 0, but the kinetic energy has got a value there. Right, so we said EK is 0 because velocity is 0, and which means EP would be mgh at A. Okay, and the potential energy is 0 again, and this is plus half mv squared. Okay, right, ladies and gents, in these, I want you to note that we are always going to have our masses cancel out if we're using mechanical energy principles. And if you note there, we end up with, if we can multiply by 2, we're going to have 2gh at A, right? Which is equal to vb squared. So we're going to take the square root. So the velocity at B would be the square root of 2 times 9.8 times the height, which is 3. And let's do that. Let's find that out. That's square root of 2 times 9.8 times 3. Right, so I get a value of 7.67 meters per second. Right, so we're going to have that as our final velocity at B. I'm going to just put it there, 7.67 meters per second. Right, now they say to us on the next one, a constant frictional force of 40.6 newtons acts on the crate as it moves from B towards C. The crate comes to rest at point C. So we know the velocity at C would be equal to 0, right? Now they say state the work energy theorem in words. Now remember, we say that the net work done on an object is equal to the change in kinetic energy, right? So they say using energy principles only, calculate the distance that the crate travels from point B to C. Now let's quickly have a look at it. We'll say, well, the net work done would be equal to the change in kinetic energy. And please note, it's always a clue that once they ask you to state a principle, you are likely going to use it in the next question, right? Now, which are the forces that are acting on this trolley as it slides, right? In this case, it's going to be gravitational force. It is going to be the normal force, but we're also going to have friction. So remember, there's no applied force in this case, right? So horizontally, the only force that's acting is the frictional force, and as such, it means that the net force is friction. So F net delta x, the cos of the angle theta, would be equal to half m, that's Vf squared minus Vi squared. Right, frictional force, that's 40.9, we were given that value, 40.6 rather, times delta x. Right, remember what's the angle between the force, or rather the direction of motion and the force in question? That would be 180. Friction opposes the motion, right? So it forms, if that's the direction of our displacement, friction is opposing that, and so makes an angle of 180. So this is going to be half of the mass of the trolley we said was 18 kilograms. Okay, so this would be 18. Final velocity is 0. Initial velocity is 7.67 We found it to be 7.67. Okay, so let's find out. So 0.5 times 18 times negative 7.67 squared. Okay, and we're going to divide by 40.6. Cos 180 gives us negative. What I do on the left, I do on the right. Okay, so this cancels out that whole thing. And so displacement that I will get there, so this is divided by negative 40.6. I get a value of 13.04 meters. Okay, so the distance that it will take for that crate to stop will actually be 13.04. I hope that that makes sense, ladies and gents. Right, and the next question, they say calculate, or rather they say the height of the track is now lowered so that point A is at a vertical height of 3 meters. The same crate is again released from point A. Okay, so let's see. All right, so we've lowered the height of the track. Okay, I'm just trying to understand here. So they say that the height of the track rather is now lowered so that point A is at a vertical height of 3 meters. It was at 3 meters, right? They say the same crate is again released from point A. How will the distance now traveled by the crate along the horizontal surface before it comes to rest compared to the distance calculated from in question 5.4? Write down greater than, smaller than, equal to, or and they want us to explain the answer. Okay, now, oh, actually I missed the part where they said it's less than 3 meters, right? For some reason my mind was just playing tricks on me, right? So in this case, definitely that distance should be less, right? Right, I can see that getting smaller. Now, why is that? Okay, so we know that the net work done is equal to the change in kinetic energy. All right, let's start with EMAC at A would be less than, okay, or let's say the mechanical energy at A would now be less than the initial one, okay? And so if it is less, therefore, it means that the velocity, the initial velocity would be less, all right? And if the initial velocity is less, then it means that the distance traveled should also be less. Okay, right, and essentially that is how we are going to explain it, right? So firstly, the mechanical energy, right, at A would be less than the one that we have in this question, and so the velocity at B, rather, I said velocity at A, velocity at B would be less, okay? And as a result, it means that the displacement would be less. All right. And essentially, ladies and gents, that is it on work, energy, and power. I really hope there's really nothing untoward here. And let's go on to the next question. And now on to question 6. They say we've got a stationary listener that records the frequency of a sound emitted by the siren of a police car when the car, which is traveling at a constant velocity of 26 meters per second, very important, okay, approaches the listener, so it's moving towards the recorded frequency is 615, right? And they say the car passes the listener at time t1 and then moves away from the listener. The recorded frequency is now 526 hertz. Right, so we've got two frequencies here. We've got the speed of the car, right? So they say to us, state rather the Doppler effect in words, okay? So please remember that definition for the Doppler effect. I'm just going to skip that and say they say to us, use the information given to calculate the speed of sound in air. Now, what I've noticed is that a lot of the times, people tend to get these calculations incorrect because of just the mathematical gymnastics involved, right? So now, first of all, let's take the scenario where the car was moving towards the stationary listener, right? So here it is, and the car is moving at 26 meters per second, right? Now, the detected frequency in this case was 615. So the frequency of the listener is 615, okay? And in this case, we didn't have the frequency of the source, right? Now, another very important thing is that we did not also have the speed of sound in air, right? And that's what they want us to determine. Right, so let's take scenario number one. So I'm going to say FL is equal to V plus minus VL over V plus minus VS times Fs, right? Now note in this case, our V is unknown, but the velocity of the listener is 0, right? So this is going to just simply be V divided by, so we've got V and Vs. Now remember, in this case, we know that the detected frequency is higher, so the kind of fraction that this must be is an improper fraction, right? And to make it an improper fraction means this has to be negative, right? Multiplied by the frequency of the source, right? Now, the detected frequency is 615, right? V is unknown, the other V is unknown. The frequency of the speed of the source, that's 26, right, multiplied by Fs. Right, so what I'm going to do, ladies and gents, is let's first try to do some gymnastics for ourselves there. So I'm going to say this is Fs over 1, okay, and we've got Vfs over V minus 26, this is equal to 615. Okay, so this would be 615, right, over 1. And if we cross multiply, so VFS is equal to 615. So this would be, 615 times, so 615V minus, okay, 615, remember we are multiplying this entire thing by 615. Right, so in this case, I've got 615 times 26. Okay, let's 615 times 26. That gives me 15990. So that's 15990. Right, I'm going to leave that as my equation 1, ladies and gents. Right, now let's go into scenario 2. So in scenario 2, this is when now the police car is moving away from the listener, right? So we know that the detected frequency should be less than or lower than that of the source. Okay, so then what's going to happen is I'm going to use the same formula, but now let me just substitute in this case. So this is going to be 526 hertz. So that's 526, which is equal to, that's still going to be V divided by, only this time it's going to be V plus 26, right? Times Fs over 1. Okay, so again, V times Fs times 1 will give me VFS, and this will be, right, if I cross multiply again, so I cross multiplied there, so this would be 526 V plus, so 526 times 26, so that would be 526 times 26, that would give me 13,676. Right, and that will be my equation 2. Now note, ladies and gents, both equations have got VFS in them. So I'm going to say equation 1 is therefore equal to equation 2. So I'm going to equate the right-hand sides. Okay, so I'm going to say, right, so 615. Okay, let's say, or you can say equation 1 minus equation 2, and nothing wrong with that. So 615V minus 15990 is equal to 526V plus 13,676. Okay, let's take all the V's together in one side. So that's going to be 615 minus 526. That gives me 89V. And I'm going to take that to the other side. So I've got 13,767, rather 676. Okay, plus 15,990. And I get 29,666. Ooh, I can hear some of you saying, oh, 666. All right. This is divided by 89. So in this case, I'm going to divide all of that by 89. And I get the speed of sound in air to be 333 well, I'll just say 33 meters per second. And that's what we get for the speed of sound in air. Usually we use 340, all right, but it does make sense for it to be 333. All right, and then let's see, any other question? They said calculate the wavelength of the sound emitted by the police siren. Now, ladies and gents, please remember this, that when I'm going to look for wavelength, this is in relation to the frequency of the source, right? So firstly, what I need to do is determine what is the frequency of the source. So let's find that first. Okay, let's do that. I'm just going to create some space here. So for 6.3, let's substitute the speed of sound into any of the two equations, right? So we've got VFS. Let's substitute into equation 1. So I'll have 333.33 Fs, right? This is equal to 615 multiplied by V, which is 333.33. This is going to be minus 15, right? So that's 15,990. Okay, so let's find that frequency of the source there, right? So I am going to say this is 615, right, multiplied by 333.33, right, minus 15,990. And in this case, all of that is divided by 333.33. Right, I am getting a frequency there. So the frequency of the source is 567. Okay, so I'll say this is 567. And by the way, another thing to check is that we'll say 0.03 hertz. Now, one thing that we need to check is that this value must actually be between the two frequencies that were given, 526 and 615, and it definitely is, right? And so now we were looking for the wavelength. Ladies and gents, we know that frequency is equal to the speed of sound divided by the wavelength, right? So please note, when you use this V here, it's not the velocity of the source, but it is the speed of sound. So I'm going to say this is 567.03 is equal to 333.33 divided by the wavelength. So we're going to just cross multiply there. So that means my answer, if I cross multiply, I'll have 567.03 lambda, right, is equal to 333.33, and we're going to divide both sides by 567. Okay, 567.03. Right, and so that is really how the cookie will crumble. Okay, so I'm going to just simply say 333.33, right, divided by 567.03. And I get a value, lambda is 0.5, okay, so let's say 59. All right, 0.59. Remember that that is in meters. That's the wavelength. It's always measured in meters. Right, and finally, let's go to the next portion. Right, so they say to us, sketch the graph of recorded frequency versus time for the motion of the car as it moved towards the listener, past the listener, and moved towards, away rather, from the listener. Label time t1 on the graph. No values need to be indicated, right? So this is going to be a very simple graph, ladies and gents. Okay. Yeah, I don't know if I could perhaps try and squeeze it somewhere. Okay, so let's just squeeze it there. Right, so there's our graph. So we know that we've got the graph of frequency against time. All right, so our initial frequency was higher. It was 6, okay. Right, so that was higher. So it was 615, okay. And what happens at time t1, our frequency becomes lower. Our frequency changes to 526. So it became 516, or rather 615 rather. And now it became 526 over there. And there is our T1 over there. All right. This is when it changed in this case. Right. So that's T1 on the graph. Right. I hope, ladies and gents, that makes sense. Right. Remember, T1 was the time where the when we passed the listener. So our frequency changed there. Of course, it's going to change gradually, but I think that should suffice for now. So that would be in hertz, that would be in seconds. And ladies and gents, that is how question 6 ends. Right, let's go on to the next question. And going on to question 7. Right, so they say to us x is a point 0.025 away from the 4 nanocoulomb point charge, as I see the diagram below. And firstly, they say draw the electric field pattern due to the 4 nanocoulomb charge. Right, so please remember it is positive. So in that case, it means that if we're going to draw the diagram showing the field lines, right, I'm just going to have this. So please remember, ladies and gents, whenever we draw these diagrams, no lines must cross each other. right? And secondly, you must show the direction. So remember that for positive charges, the field lines would be moving away. Remember, the field lines actually are showing us the direction that a point charge, a positive test charge, would actually move relative to that charge there. So it would be repelled, whichever way you look at it, in any direction, we would actually repel that positive test charge. So that is how the diagram would look like. Nothing wrong with placing the arrows, okay, or the heads of the arrows right at the end over there. Nothing wrong with that, okay? So please note that the lines must not cross each other, all right? All the lines must be connected to the center, right, of that charge in that case, all right? And we must always show the arrows. Now, they say to us on the next one, they say calculate the magnitude of the electric field at point X. All right, so for the magnitude of the magnetic field, electric field, we say E is equals to KQ divided by R squared, right? So in that case, that's 9 exponent 9 multiplied by the charge, which is 4 times 10 minus 9, that's nano, divided by the distance, and our distance is 0.025. And remember, we square that distance, and so if we do that, so that's 9 exponent 9 multiplied by 4 exponent, okay, we did something wrong there. That's 4 exponent negative 9, and all of that is divided by 0.025, but remember that we are going to square that, and so that gives us 57,600 newtons per coulomb, right? And by the way, they had just said the magnitude of it, okay? They didn't require direction, so we're going to just leave it at that. Right, next question. They say two identical neutral polystyrene balls, A and B, are suspended from a ceiling by insulated light inextensible string of equal length, as shown in the diagram below. Right, now they say to us ball B is given an initial negative charge, right, of unknown magnitude. The balls attract each other, okay, and then repel each other. The balls come to rest with their centers 10 centimeters apart, so that each string makes an angle of 9 degrees with the vertical. See the diagram below. Now they say stating Coulomb's law in words. Ladies and gents, I'm not going to waste much time on the definitions. I believe at this stage you should know those definitions, right? So let's get to the next part of this question. They say calculate the magnitude of the initial charge QB, right? Given to the ball B, if the mass of each ball is 0.012 kilograms. Now, ladies and gents, let's do this. What we can do is draw, in this case, a force diagram showing us the force of all the that's acting on ball B. So let's start with ball B. So in this case, so we're drawing a force diagram of that. So we know we'd have the tension on the string. Okay, so we'd have the tension on the string there. All right, and we would have, remember they are repelling each other, so we'd have the electrostatic force, or you can say the force of repulsion. And then finally, we'd have the gravitational force there. Right, so we know we'd have the weight of these guys, right? So those are the forces that are acting And I know that this force is actually acting at an angle of 9 degrees to the vertical, right? So we can find out what is the electrostatic force. So in this case, the force of repulsion, right? Remember, how can I do that? Well, there's a triangular law of vectors that are in equilibrium, okay? And that law simply says if we've got three forces that are at equilibrium, they can be represented by a triangle, right? And that triangle with each side taken in order of its magnitude and direction. So this would be the weight, right? We know that's downwards. This would be the force of repulsion, right, for B. So I'm going to say Fr, and this would be the tension. Now, remember, we can find out what the weight is because we know the mass that is given to us, right? So they told us that the mass of each ball is 0.012 kilograms. So the weight would be 0.012 times 9.8. Now let's calculate that. 0.012 multiplied by 9.8. Okay, so I'm going to take that value okay, I'm not going to round it off. 0.1176 newtons. So that's the value of the weight of the balls, right? Now, I can find out now using trigonometry. Now note, ladies and gents, this is a 90-degree triangle, right? So this side over here, now please stay with me, ladies and gents. This side is my adjacent side, and the side that I want, the force of repulsion, is my opposite side. It is directly opposite to my angle, right? So in that case, what this simply means is that in order for me to find Fr, I can say, well, the tan of 9 degrees would be equal to Fr opposite over the adjacent. Okay, so remember that's opposite, which was Fr, and the adjacent side is the weight. So to find the length of Fr, right, the repulsive force, force of repulsion, okay, let's call it F repulsion. This is going to be the weight, which is 0.1176 multiplied by the tan of 9 degrees. All right, so let's find that. 0.1176, the tan of 9 degrees. I'm going to leave that answer there. Okay, so that gives us 0.01, let's say 19, right? Let's say 0.019 newtons. So that's the the force of repulsion. Okay, so now, ladies and gents, what can that possibly do for us? Using Coulomb's law, we can now find out what is the charge on B. But that would give us the charge of B afterwards, right? So let's now quickly find out, okay? What would be the net charge? And so as a result, we can now find out what was the charge of B initially. So firstly, I'm going to say, right, we know the force, right? So the force between A and B, that's KQA, QB. But remember, after they started repelling each other, their charges would have been equal. Remember that whenever we bring two spheres or two objects together that are equal, in this case in terms of dimensions, right, they will share whatever charge equally, right? So which means the charge of A should be equal to the charge of B. So in this case, I know that the force that they have is that 0.019. I'm just going to take the, okay, that's 0.019, that's 9 exponent 9, right? I'm going to say charge of B squared, because charge of A and B are the same, divided by their distance. The distance is 10 centimeters. Now remember, ladies and gents, you need to convert that. So that's 10 centimeters. So you can say 10 divided by 100, or you can just simply say 10 times 10 minus 2, right? So I'm going to say 10 divided by 100, which should give us actually 0.1. Okay, so that would be 0.1 squared. Right, ladies and gents, I'm going to take that value. Since I have it, I still have it, right? I'm going to say, right, cross multiplied by 0.1 squared, okay? And I'm going to divide by 9 exponent 9, okay? I get a value there, and remember, to get the charge, I need to now take the square root of that answer. All right, let's do this. So I get 1.44 times 10 minus 7. I hope that's correct, ladies and gents. Okay, so the charge on B afterwards, so this would be the charge on A and B. That would be 1.44 times 10 minus 7, okay, coulombs. So that's what I get in terms of their net charge afterwards. Now we need to remember, what were we looking for? For the initial charge, not the one after they touched each other, right? So this would be the net charge on the two balls together, right? So now I need to find out the charge on B, the initial charge on B. But remember, what was the charge on A? The charge on A was 0. Okay, so remember, they say ball B was given a negative charge. Okay, so remember, so it means that this net charge on ball A and ball B in this case would be negative 1.44. So now we need to find out what was the initial charge. So whenever we're finding net charge, Q net, it will always be QA plus QB divided by 2, the number of charges that were there, right? So Q net is negative 1.44. All right. The charge on A, right, was 0. Remember, they were neutral, so which means that a neutral charge is 0 charge. The charge on B divided by 2. And ladies and gents, if we do our gymnastics, right, that's over 1. So therefore the charge on B would be equal to twice that amount of charge. So that would be negative 2.88 times 10 negative 7 coulombs. I hope that makes perfect sense, ladies and gents. And essentially, that is really how the cookie crumbles. All right, that's how you would answer that question over there. Right, nothing wrong if you decided to use components of a force there, right? So you would have said the vertical component of that tension would be equal to the weight in that case. And you can find yourself that vertical component, you find the tension, and you can find the force of repulsion. I just think that the triangular method is really much neater, okay? And so for me, it always is the option. Right, ladies and gents, let's go on to the next question. And now on to question number 8. They say to us, we've got a battery with an EMF of 12 volts and an internal resistance of 0.2 ohms, which is connected to 3 resistors, a high resistance voltmeter, and 2 switches, an ammeter, and connecting wires of negligible resistance, right, as shown in the circuit below. They say that 3 resistors have different and unknown resistances, right? So that's very important. So the resistors are different from each other. Right, now let's look at this. So they say to us, the resistance Ry is twice the resistance Rx. Now what I would do, ladies and gents, is that, look, if I call Rx, okay, well, let's leave it as Rx, which means Ry would be 2 times Rx. Okay, right, now they say to us, when both switches are closed, the reading on the ammeter is 5.5. Now let's look at the ammeter. So our ammeter there reads the total current. We're going to come to that just now. Okay. Now they say to us, give a reason why there is no current through RZ. Very important. Now, ladies and gents, I want you to note, of course, we're going to have total current passing through the circuit, right? What happens when we get to that node? Remember, no current passes through the voltmeter. So we'll have some of the current dividing, going into Rx. We'll have some of the current going into Ry, right? But at that node again, we've got the total current, the red current. But now why does it bypass Rz? Okay, because remember that current will always take the path of least resistance. So in this case, what that simply means is that there's actually less resistance here. There's actually no resistance at all. So all the current would actually take that route over there. All right. So that is why there will be no current passing through RZ. Okay. So they say give a reason why there's no current passing through RZ. We say that that current, or rather that resistor, is short circuited. Okay. So because resistor RZ has been short circuited, right? So we call that a short circuit when we connect a wire across a resistor. Okay, right, ladies and gents, let's now go to the next one. They say calculate the resistance of Ry. All right, so before we calculate Ry, let's calculate Rx. So what I'm going to do is, remember, we've got the EMF. Okay, we've got our total current, we've got the internal resistance, right? The only thing that we do not have in this case are our resistors. Now, because they're in parallel, so remember that Rp would be equal to, so we always say product over sum if it's two resistors, right? We can say 1 over R1, 1 over R2, but in this case, we can say, well, this is going to be Rx times Ry divided by Rx plus Ry. So my Rx value, right, that's going to be Rx, but Ry is 2 times Rx divided by Rx plus 2 Rx. Right, so what does that give us? So this would give us, okay, so let me just write it over here. This would be 2Rx squared divided by 3Rx. And so what happens? This Rx cancels out one of the Rx's there. And so we end up with 2 over 3 Rx. This is our parallel combination, or this is our external resistors, right? So now what I'm going to do is use my EMF formula and say E is equals to I into R plus small r. But remember, this would be total current over here. This would be total resistance, the external resistor rather, in this case, or the resistor of the load. So this is 12. That's 5.5. This is 2 over 3 Rx. And this is plus the internal resistor, which is 0.2. All right, and let's do our gymnastics over there. So I'm going to divide both sides by 5.5. Okay, and I'm going to subtract the 0.2. So this is going to be 12 divided by 5.5, and I'm going to subtract the 0.2 for the internal resistor, right? Now we end up with 2 over 3 Rx. Okay, so I want to write 2 over 3 there. Rx is equal to that value, 1.98, and so on, right? So now what do? I multiply by the inverse, right? So I multiply by 3 over 2 to get rid of that. Cancels with that, that cancels with that. But remember, what I do on the left, I do on the right. So I'm going to take that value and multiply it by 3 over 2. And so I get a value of Rx, ladies and gents, of 2.97 ohms. Okay, so that would be the resistance of Rx. But remember, they said to us we must find Ry. So we know that Ry is 2 times Rx. So it will be 2 times 2.97. Okay, so I'm going to take that value. Okay, I'm not sure what happened there. Okay, so I'm going to say 2 times 2.97, and I get 5.94. So that would be 5.94 ohms. Okay, let's write that nicely. Right, so that is what we get for the resistance of Ry. Okay, so they say calculate the power dissipated by Rx. Now remember, in this case, for Rx, what would we know in that case? Well, for Rx, we actually know, in fact, the total current of the circuit is 5.5 ohms, right? So we don't even know the resistance of the two resistors. However, do you remember we said that Rp, or the parallel resistors, would be, in this case, so for Rp, that would be the parallel resistance, which is 2 over 3 Rx, right? So which means if I want to find that Rp, that I can now use that formula there. So Rp would be 2 over 3 multiplied by, you remember Rx is 2.97, so that would be 2.97. Okay, so let's calculate that. That's 2 over 3 and multiplied by 2.97. Okay, so 2.97. Okay, and I get a value of 1.98. Okay, so that was 1.98 ohms. That's our parallel resistors, right? But now remember, so what I'm going to do is I'm going to look for that voltage V, right? So let me find out what V is. And once I can find out, remember that in parallel, voltage is the same, right? So I'm going to simply say, if I take those two as one resistor, they give me an effective resistance, parallel resistance of 1.98, okay? And that 1.98 resistance, in this case, would have a total current of 5.5 passing through it. So I can now say the voltage V is actually equal to, that's going to be I multiplied by R. Okay, so that would be I total multiplied by R parallel. So this would be 5.5 multiplied by 1.98 volts. Right, so let's find out what that is. So this would be 5.5 multiplied by 1.98, and that gives me 10.89 volts, right? So that's the voltage there. But remember, what did we say? We said it means the voltage there would be 12.89 as well, right? The voltage there would also be 10.89 volts as well, right? So, ladies and gents, let's find out what is the power that is dissipated. We know that power is equal to V squared divided by Rx, right? So the voltage, 10.89 squared divided by the resistance of Rx, right? We said Rx is 2.97. And in this case, what do we have? So that's 10.89 squared. That's divided by 2.97. And so that gives me a total power dissipated of 39.93. And remember, power is measured in watts. And I'm sorry that I had to squeeze that in there. You could have also calculated this by finding the current. There's a very nifty way of calculating the current passing through parallel resistors, particularly when you know the current, the total current, right? What you can do is say, well, the current across, right? So we wanted across Rx, right? But now the current across Rx, you always use the resistance of the other resistor. It will be Ry divided by Rx plus Ry, okay, multiplied by the total current. All right, so Ry was 5.94 divided by the sum of the two, which is 2.97 plus 5.94, okay, multiplied by 5.5. I'm just showing you this, ladies and gents. You can use it or not use it. It's really up to you. Okay, so just to show you that we'll get to the same answer. So this would be 5.4 divided by 2.97 plus 5.94 again. Okay, and this is multiplied by 5.5. Okay, so we get a current of 3.66666666. So that is now our current through Rx. But remember, to calculate power, you say I squared. So I'm going to square that value, right? Okay, multiplied by the resistance of Rx, which is 2.94. Right, and I'm going to multiply that by 2.94, and there we have it. You get 39.53. Of course, there should be a little bit of a discrepancy there because of the rounding off, but it essentially we should be able to get to the same answer. All right, I hope that makes sense, ladies and gents. All right, and so many people complained about this question. Right, and let's go to the next one. Now they say both switches are now opened, right? The reading on the ammeter is 1.3. Now, if I am going to open both switches, now I want us to quickly have a look at it. Once I open switch S2, it means there will be no current that is flowing here, right? So Rx is gone, right? And then if I open the switch S1, then it means this switch is no longer there. So I'm left now with total current passing through Ry, and then total current passing through Rz. Now they say to us that the total current now becomes 1.3. So we no longer have the 5.5. We've got 1.3 amperes that will be passing there. So now they say to us, calculate the reading on the voltmeter. Very important, ladies and gents, right? So again, we've got the total current, okay? the voltmeter reading will be the reading only on Ry this time around, right? So I'm going to say, right, for that value, I'm going to have, okay, let's do this. V is equal to I multiplied by R. Okay, and that would be I total, which is 1.3, multiplied by Ry. Remember, Ry has not changed. That is still 5.94. Okay, so that would be 1.3 times 5.94. And I get a value of 7.72 volts. Okay, so that's our voltage reading over there. Right, and now they say to us, so switch S1 remains open. Ooh, we're dealing with so many gymnastics here. So switch S1 remains open. Okay, so so switch S1 is still open, which means we still have current flowing through RZ. And then they say to us, calculate the reading on the emitter. All right. Actually, they said switch S1 remains open while switch S2 is now closed. So S2 is closed, so which means again, we've got our parallel combination back, right? R1 and R2 in parallel, but we've got now RZ as well, right? And they said to us we need to calculate the reading on the emitter. Now, ladies and gents, we need to be very mindful when we do this question. Okay, I'm going to try and squeeze everything in there, but let's see how far we get. Now, I want you guys to be mindful that we've got our parallel resistance, but we've got now resistor RZ, which is now unknown to us, okay? And the current can no longer be that 1.3 that we had. Why? Because we've actually changed the circuit, right? So we've got 3 resistors now instead of the 2. However, what remains the same in the circuit is the EMF as well as the internal resistance inside the battery, right? So now what are we going to do? We're going to say, right, for the first thing is let's try and find out what is the resistance of RZ. Okay, so I'm going to say E is equal to I into R plus small r. Okay, so our EMF, this is 20, this is 12, sorry. This is 12, right? Our current is unknown for now. In fact, you know what? Let's actually take the previous scenario. Let's take the scenario before where we knew the current value. Our current was 1.3, right? And what was our resistance? Our resistance was Ry as well as Rz, okay? So it was a series combination. So I'm going to just say R series, okay, plus our internal resistance, which is R 0.2, right? So we can find out what Rs is, okay? So that's 12 divided by, so remember that's 12, okay, it just doesn't look very nice. Okay, so I'm going to do that all in the calculator, ladies and gents. I expect you to be able to do the same. So that's 12 divided by 1.3, right? Now I've got Rs plus 0.2, so I'm going to subtract the 0.2, and that means I've got 9.03. So R series is 9.03 ohms. Now, ladies and gents, please note, right, that now, what did I have? When I had both switches closed, remember that we had Rx not functioning. So we're left with Ry, which is 5.94, and Rz. So these two were the resistors that we had. So R series was equal to Ry plus Rz. So we know the value of R series. So therefore it means that RZ would be equal to 9.03, which is the total resistance there. So that would be 9.03. And we are going to subtract the value of RY, which is 5.94. Okay, so that gives me 3.09. So RZ is 3.09 ohms. Okay, so that is the resistance of that resistor. Now, remember we are now looking for the current. Okay, so let's go to scenario number 2, where we now closed both of our actually we closed switch S1 is open. So remember, when S1 is open, okay, so S1 is open, right? So which means the current would go through RZ. That's why we wanted to find out RZ. But they had said to us S2 is now closed. So once we close S2, remember we have our parallel resistors back. All right. So let's find out what R external will be. Okay. So which means R external would be a combination of that parallel combination. By the way, we already have our parallel. It was 1.98. You remember we found that, right? So R external will be a combination of that parallel resistors, right? So it will be our parallel resistors, but remember the combination of them will be 1.98 plus RZ, and we just found out this is 3.09. So let's say R external, okay, so remember those would be in series now, would be RZ plus R parallel. So that's 3.09 plus our parallel was 1.98. Okay, and so what do we get there? So 3.09 plus 1.98. And so, no, actually, we made a mistake there. 3.09 plus the 1.98. And we get 5.07. Okay, and this is our resistance of the resistor, the total resistance, right? And now to get the current, what can we do, ladies and gents? Remember, EMF still remains the same. So E is equals to IR plus small r. And ladies and gents, we know this still remains 12. We want the total current. The resistor is the resistance rather 5.07 plus small resistor R, that's 0.2. Okay, and in this case we're going to say 12 divided by the total of 5.07 plus 0.2. And in this case, ladies and gents, we are going to get that current to be equal to 2.28. That's 2.28 amperes. And we've tried to really get everything in there, right? I hope that you guys were able to understand all of that. I see why so many people were complaining about this, but I hope that you were able to follow on. And if need be, you can rewatch this again. All right, so we are going to move on to the next section. And now we hop on to question number 9. They say the simplified diagram below represents an AC generator with a coil rotating clockwise. X and Y are 2 points in the external circuit. All right, and they say to us, what is the direction of the current in the external circuit? Write either X to Y or Y to X. Now, very important, ladies and gents. So what I'm going to do is, let's look at on this here, but let's actually compare where is the current moving. Let me label that, let's say AB, right? So if you look at that, remember, if I'm rotating clockwise, it means on side AB, that side is actually moving upwards, right? So please note, that is moving upwards. And so it means my thumb will be pointing upwards, right? And then secondly, we know that field always moves from north to south, okay? So the direction of our magnetic field will always be from north to south. That will be where your forefinger is pointing. So we know that it will, first of all, we know that my thumb would be pointed upwards, right? Your first finger will be towards by the way, we're going to use our right hand, right? This is going to be, because we're dealing with a generator, we use our right hand. And so you'll see that if you do that, your second finger will actually be pointed in that direction, okay? I don't know how to do that. I'm just trying my level best. I always say, if need be, I can actually try to save my own life, with the drawing. So there it is. That would be your middle finger, right? It would be pointed in that direction. So what does that show you? Shows you that current would be going from A to B. And if it's going from A to B, then it would be going from Y to X, all right? Because it's circulating like that. Okay, so it will be going from Y to X. So that is it there. All right, so let's go to the next question. They say, state the energy conversion that takes place in this generator. So remember, what does a generator do? It converts mechanical energy, right? Energy into electrical energy. To electrical energy. This is just me being lazy, okay? But I know you will write it in full. Right, so next question. They say the maximum voltage produced by this generator is 125 volts, okay? And they want us to define the term, the mean square voltage, the root mean square voltage, okay? As I said, I'm not going to bother with the definitions. Please make sure that you know these definitions and you learn them, okay? Now they say to us, calculate the root mean square voltage for the generator. So we know, how do we get VRMS? We know VRMS will be Vmax divided by square root of 2. We're given there that the maximum was 125. So this will be 125 divided by the square root of 2. And so what that gives us is, okay, that's square root of 2. And that will be 88.39. Okay, so that's 88.39 volts. So that's our RMS voltage. Okay, so the next question says, calculate, or rather they say the total resistance in the external circuit is 42.4, right? And they want us to calculate the maximum current induced. Now remember, when we use maximum, when we want maximum current, we need to use maximum voltage, right? So we're going to use Ohm's law as we know it. So Vmax will be equal to Imax times R, right? We are looking for Imax. And so as a result, what are we going to do? Our Vmax is 125, right? Our Imax is what we're looking for, but our resistance is 42.4. Okay, so if I divide by 42.4 on either side, okay, and so what I get there is 125 divided by 42.4, I get 2.95. Okay, so my Imax value my Imax value would be 2.95 amperes. Okay, right, I hope that makes sense, guys. And then they say to us, the generator induced current at a frequency of 20 hertz, right? And they say the coil started rotating from the initial position as shown in the diagram above. All right, so there we are from that initial position. Right, so remember, from this initial position, we can see that we are actually going to start. So remember, when we've got field is moving in that direction, right? Now, if you note there, your armature is actually parallel to the field, and so our force in that case will actually be at the minimum, right? All right, so in that case, we're going to start at 0. All right, and then we are actually going to have a maximum once we get to that 90-degree mark. So as a result, ladies and gents, they said to us it is 20 hertz. I'm going to show that there. Okay. So they said the coil started rotating from the initial position as shown in the diagram above. Sketch a diagram, a graph rather, of induced current versus time for 2 complete rotations of the coil, right? Indicate the following on the graph, all right? The time taken for the rotation. So remember, so for the first rotation, we're going to start from 0. Okay. And we're going to have another rotation there. So for one full rotation, remember, we're talking about alternating current here. So as a result, this is what's going to happen. Right. So for one full rotation, we'll have maximum and minimum, right? And we know that our maximum value for the current, we said that was 2.95. Okay, so that will be 2.95. That will be minus 2.95. Okay, so this is going to be current, okay, in amperes. All right. And then now they told us that the frequency is 20 hertz. So which means, now please note, ladies and gents, that period is 1 divided by frequency, right? Now this is how long it takes for one full cycle. So this is going to be 1 divided by 20, and that should give us 0.05, right? Okay, so that's 0.05. And so they say the time taken for 2 rotations, so that's 0.05 multiplied by 2, that's 0.1. So the time here should actually be 0.1 seconds. Okay, so this time here should be 0.05 and the other time should be 0.1. Right, I hope that makes sense, ladies and gents. Essentially, this is how we were going to get full marks here onto this section. Right, we'll go on to the next one. And finally, question 10, they say define the term photoelectric effect. As I said, I am not going to bother much into that. Okay, let's go to the calculations. Please learn all of these definitions. Ladies and gents, let's go on to the next one. They say light of wavelength 4.7, exponent minus 7 meters. So we've got the wavelength there. Is shown on the surface, onto the surface of a piece of cesium metal. If the threshold frequency of cesium is 4.37 times 10 to the power 14, they say calculate the maximum speed of an electron ejected from the surface of the metal. Now, first of all, ladies and gents, we just need to note there that we are given also the threshold frequency, which means we can work out the work function. of that metal, right? So I'm going to say, right, so E is equal to omega 0 plus EK max. Okay, so firstly, we've got HC over lambda, because we're given the wavelength, right? And we've got HF0, and we are looking for the maximum speed. So I'm going to say this is half mv squared. Okay, right. Okay, let's just say half mv squared. So let's substitute there. This is going to be 6. Okay, so that is going to be Planck's constant. That's 6.63 times 10 minus 34 multiplied by 3 exponent 8 divided by our wavelength is 4.7 times 10 minus 7. And this is equal to, right, I'm sorry, I'm not going to be able to fit everything in there. Let's see if we've got space at the bottom. Actually, we could have used that space at the bottom there. If you don't mind, yeah, I'm just going to do that. Okay, so this would be 6.63 times 10 minus 7, okay, multiplied by the speed of light, okay, divided by, we said the frequency, rather the wavelength was 4.7. So that's 4.7 times 10 minus 7. And this is equal to, again, 6.63 times 10 minus, I said minus 7 for some reason there. That's minus 34. Okay, that's minus 34 multiplied by, now the threshold frequency that we were given, right, is 4.37 times 10 to the power 14. So that's 4.37 exponent 14 plus, now our EK max, ladies and gents, please note, this would be the mass of an electron, which is 9.11 exponent minus 31. Please note you are given that mass of an electron. There it is right there. Okay, right, so that's the mass of an electron multiplied by the speed squared. Right, so let's do that all in our calculator, ladies and gents. Start with the first thing, 6.63 exponent minus 34 multiplied by 3 exponent 8 divided by, got 4.7. All right, so we've got our answer there. And we're going to subtract from this, this work function, which we get by saying 6.63 exponent negative 34 multiplied by 4.37 exponent 14. Okay, and now we get that final answer there, and we are now going to divide by half the mass of an electron. So divide all of this by 0.5, I'm going to put it in brackets, 0.5 times 9.11 exponent negative 31. All right, ladies and gents, I'd really love for you to assist on this one. Okay, so I've got my final answer there. Apologies about that. And then I'm going to just simply take the square root, remember, of our answer, right? And what do we get there? I get a value, so let's just take the, scientific form of it. So I get V to be equal to 5.41, okay, exponent 5. This is in meters per second. So that would be the speed of the ejected electron. All right, I hope that makes sense. Right, now the next question, they say we've got a simple electrode that consists of a zinc disc, a metal stem, and a thin length of gold foil, right? They say when the electroscope is neutral, the foil hangs vertically, as shown in diagram 1 below. When the electroscope is negatively charged, okay, so in that case, they say the foil is repelled by the stem as shown in the diagram, right? And so they say when ultraviolet light is shone on the disc of the negatively charged zinc electroscope, the foil collapses towards the stem, right? That is, it hangs vertically. All right, now, so they shone ultraviolet light, so it was negatively charged. They shone ultraviolet light, and then it caused this guy to collapse, okay? Right, now they say to us, how does the frequency of the ultraviolet light compare to the threshold frequency of zinc? Write down higher than, lower than, and or equal to. Now, let me just explain what happened. Now remember, it was negatively charged, and the moment we shone ultraviolet light onto this, so those electrons now were ejected, right? And so what it does, because electrons are ejected, it causes for there to be no electrons. And so they said if it's neutral, it will actually just collapse back, right? So that means that the work function, or rather the frequency, right, of the ultraviolet light would be greater than the threshold frequency. So in this case, we'll just simply say higher than. All right, so they say explain why the foil of the electroscope collapses. Right, so we will just explain that ultraviolet light has got photons which have a greater amount of energy. So the energy of the photons, apologies there. So the energy of the photons of ultraviolet light is greater than the work function, right, of the electroscope, right? And so as a result, electrons are ejected, right, causing the electroscope to be neutral once again. And we know that when it is neutral, it will collapse. Okay, so you can write all of that down, but it boils down to the photoelectric effect yet again, right? That electrons are ejected in this case. Right, and then they say to us, green light is now shown on another negatively charged zinc electroscope. The foil does not collapse. Clearly, it says that green light has got the energy of the photons of green light would actually be less than the work function in that case, right? Now, they are asking a question, will the foil collapse if the intensity of green light is increased? Absolutely not, right? No, it won't. They say write either yes or no and give a reason for the answer. Right, so intensity, right? So increasing intensity will not increase, in this case, the energy of the photons of green light. So remember that energy of the photon is proportional to the frequency. So the frequency of green light would still remain the same, and as a result, it means that the energy of green light would still be the same, right? And as a result, it means that no electrons will be ejected. All right, I hope that makes sense, ladies and gents. And really, we come to the end of this question paper. I really hope that it was really helpful towards you, or rather to you, to go through this memo. For those of you who are going to be writing your final, not your final rather, but your June exams, for those of you in Matric, I hope that you'll be able to look at this. But also for those of you who are writing the May, June exams, right, who may feel that you need to rewrite again, I hope that this will be helpful. Otherwise, ladies and gents, from me for now, I'll see you guys next time. And please don't forget, if you need to get in touch with us, our details are on the description of this video, right? And I'll continue to give you good content in maths and science. Otherwise, ladies and gents, I'll see you guys next time. Shap shap.